Today, we want to move on to the next big thing in calculus, or the usual big thing that comes after derivatives, and that would be integration, which is just derivatives going the other direction. Plenty of time to talk about how we're going to calculate integrals. The good news is we've already done all the calculating of integrals that we need to do back in Calc 2. We just need to modify those calculations to deal with functions of more than one variable. But also running in the background, we need to think about how we think about integration. So here's the way I like to think about integration. Integration is multiplication in which one of the factors is continuously variable. That's what makes it a calculus problem. One of the factors is continuously variable. Multiplication is just addition where all the things are the same. That's why we get to multiply. So for example, we've got 5 plus 5 plus 5. That should mean that we just write that as 3 times 5. It's addition, but it's a bunch of the same thing. So we get to multiply. If we have addition, but the terms are not all the same, we have addition, but the terms aren't all the same, we don't get to multiply. Terms aren't the same, we don't get to multiply. When the terms aren't all the same, we don't get to use multiplication. We just have to stay with addition. Multiplication is like an upgrade. But with 5 plus 6 plus 7, we just have to stay with addition. Here's a sum where the terms are different, but this sum is a discrete sum. There's a first term, a second term, and a third term. Where calculus enters into it is where the terms in our sum are not discrete, are separated. Where one of the factors in a multiplication problem is continuously variable. And that's why that's where we end up with Riemann sums. So we take the limit as n goes to infinity of the sum I goes from 1 to n. We model the continuous sum with the discrete Riemann sum, and then we take the number of terms to infinity. And that should give us our continuous sum, which we represent with a definite integral. So we model our continuous sum with the discrete sum in the Riemann sum, and that's let the number of terms go to infinity. So what we want to happen is we want the continuous sum so the continuous sum is modeled with a discrete sum. Are there 2 L's in model? Model-led, or is it just model? One of those words, no matter how I write it, it's wrong both ways. Hey Siri. How do you spell modeled? 1 L. I'm surprised. I shouldn't be surprised that I got it right. I mean, it's a word that I write every semester, but there it is. So we have a definite integral will represent our continuous sum. It's because one of the factors is continuously changing. Over here, 5 plus 6 plus 7, this is a discrete sum. The discrete sum has a next term, the continuous sum does not. So for example, when I go to add up all the points that everybody has, it's not going to be the same. So I don't get to use multiplication, but it's not going to be continuously variable. Each individual has a certain number of points. So there's just going to be 19 terms in that sum for the total class points. Any questions? The reason that we need to talk about this is because we're going to talk about integration. And we need to think about what integration can be used for. And integration can be used exactly for this, among other things, but exactly for this. Integration is multiplication in which one of the factors is continuously variable. So the ones that we typically start off with are area is equal to length times width. We find area under a curve. Another one that we use is distance is equal to rate times time, and then we have a variable rate over time. And so we have to integrate because our rate is changing continuously. Way back in Calc 1, we calculated volume as cross-sectional area multiplied by height. So back in Calc 1, we said volume is cross-sectional area multiplied by height. Volume is area times length. That makes sense. Area is squared units, height is linear units. That gives us linear units cubed. That's how we measure volumes. So volume is area of a cross section multiplied by the height. It's just a multiplication problem. Here was our limitation in single variable calculus. In single variable calculus, the area of the cross section always had to be the same shape. So in Calc 1, the area of the cross section always had to be in the same shape, and we had to write it as a function of the height, because when we did this calculation in Calc 1, the height was, or Calc 2, the height was our delta variable. So the height is the part that gets infinitely small so that we can view a volume as a stack of areas. So the usual deployment in Calc 1 is that height back in Calc 2, height was usually our delta variable. Here's what I mean by delta variable. That is the dimension that has to get infinitely thin so that we can have a stack of areas. So if you haven't been in my class before, that's why I have to define the words that I use a lot. And I like to talk about the delta variable. The delta variable is the dimension that's getting infinitely thin. So the delta variable, that is the one that has to get infinitely thin so that our volume is a stack of areas. So if you'll recall, we do things like find the volume of a cone, even though we know what the volume of a cone is. We're going to imagine the cone as a bunch of cylinders. So the cone is just going to be a stack of cylinders. I'll draw a side view. We got a 3/4 view and a side view. But we're envisioning the cone as a stack of cylinders. Then we got to increase the number of cylinders to make it look more like a cone. We've got to increase the resolution, and the delta variable is the part that has to get infinitely thin, so I can have an infinite stack of cylinders. So that thickness of each cylinder is our delta variable. Back in Calc 2, the area of cross section always had to have the same shape. It had to be circles all the way up, or squares all the way up, or I don't know, whatever huge variety of shapes you always have. Because we want to take the area multiplied by the height. We were allowed to vary the value of the area, but we were not able to vary the shape of the area. Because we wanted to be able to say something like pi r squared times h. And then we wanted h to be the delta variable. Here in Calc 3, we have more freedom because we're going to use more variables. We're still going to imagine volume as the area of a cross section multiplied by the heights. That's not changing. We are still going to imagine the volume as the area of a cross section multiplied by the height, but we're going to switch things around. Rather than the area of the cross section being the function and height being the delta variable, we're just going to flip those. The area of the cross section, that's going to be our delta variable, and height is going to be our function. Now, because the area of a cross section is a two-dimensional thing, it's an area, not a length. Two-dimensional, that's going to have to be two-dimensional, which means our height is going to have to be one-dimensional. So we are still doing area of the cross section multiplied by the height, but this area is going to be the delta variable. So in Calc 3, the area is going to be the delta variable. And the height is going to be the function. Where? Oops, that's where it's coming from. In Calc 3, the area will be the delta variable. I don't have a good lighting rig for this. So it's a little shiny until it dries. Since the area is two-dimensional, that'll have an x and a y. Our height is going to be a function of two variables. Questions? So rather than thinking of the area of a cross section times height, we're going to have the area of a cross section times the height. But we're thinking of it differently. I know it sounds like I said the same thing, but I totally didn't. In the first one, I said where the area of the cross section multiplied by the height, and I was thinking that was the delta variable. But in the second one, it's the area that's going to be the delta variable, and the height will be a function of two inputs, x and y. So here's how we're going to think of finding the volume under a surface and above a region in the xy plane. Any questions before we go on? From here on out, the calculation is going to look the same. I'm going to use the value of the function at a certain point as the height and think that that height is constant for some small patch of area. Just like in integrating a function of one variable, the technique is to assume that the length is constant for some small change in the width, and then we get to use multiplication. We'll do the same thing here. We'll assume that the height is constant for a small change in area, and then use multiplication to calculate the volume. So we'll assume the function is constant. That small change in area will be a dA. Change in area. Once the height is constant for some small change in area, then we get to multiply the height times the area. So the area of a piece of one rectangular solid is going to be f at xi, yi, the heights above a certain point, multiplied by the area. Then we'll move on to a different area, recalculate the height, multiply, and that'll give us the volume. Add up all those volumes, then let the number of rectangles go to infinity, make the dA infinitely small. Any questions? How's everybody okay? So let's imagine our X, Y, and Z axis. So in the XY plane, we'll have some point xi, yi, and then we'll calculate the height of the function above that point. I missed a little bit. Now we're imagining this is one point on a surface, and the surface is changing continuously in the x direction, continuously in the y direction. But we want to make our algorithm work. We want to develop a Riemann sum. So I'm going to say that's the value of the function for some small area around the point I care about, for some small change in area. So the dA is going to be some small area, some small square, rectangle, in the xy plane. The size of the dA is going to be the change in x multiplied by the change in y. So there's going to be a dx and there will also be a dy. So the area, the dA, is going to be dx multiplied by dy. And we're imagining that dA all the way up to the height make a rectangular solid. And that's going to be the volume of our first rectangle. I usually refer to, when we cut up a region or a solid into a bunch of slices, I refer to the slices as slices. So when I cut a volume into a bunch of rectangular solids, I refer to the rectangular solids as slices. So the volume of the slice will be the height evaluated at that one particular point, f at xi, yi, or yj, multiplied by the area. And the area is just dA. But we're going to read the area as dx times dy. So I can write f at xi, yj for all the x values, so dx, and all the y values, dy. I was doing the same thing earlier and mixing my deltas and my d's. Delta A. We're still in the discrete case. And there'll be a delta x times delta y. Now that's going to be the volume of one of these rectangular solids. And I'm going to break this up into, let's say, m x's and n different values of y. So I'm going to have to do a double sum to get the total volume. So the total volume is not only going to be the sum as f of xi, y, j. Oops, that's not a j hat. Those are just indices. I'm going to have a double sum, one for the index I and another one for the index j. So let's run the x's as I goes from 1 to m and run the y's as j goes from 1 to n. So it's the same procedure, the same assumptions, the same operations that we did in the Riemann sum for a function of one variable. Then all we have to do is do the same thing that we did when we had functions of one variable. Our double Riemann sum will become a double integral. An integral for the x's and an integral for the y's. We get there by taking the limit as I and j go to infinity. That's how we make our discrete sum into a continuous sum. We make the delta x, delta y infinitely small. So our double Riemann sum is going to turn into a double integral. Since we're going from a discrete sum to a continuous sum, we can drop the indexing. Instead of f at xi, yj, it's just f at xy. We're switching to continuous. Since we're switching to continuous, instead of delta x, we would write dx. And instead of delta y, we'll write dy. Now the double integral is just going to tell us what values of x and y to plug into this calculation, f at xy times dx dy. We want to make sure things line up proper. So that first integral symbol, or the integral symbol that's closest to the function, is going to correspond to the dx that's closest to the function. So this inside integral will be x values. So this will tell us that x goes from a to b. And since dy is the outside integral, the outside integral will tell us that y goes from, say, c to d. So we want to make sure that each of those two integrals corresponds to the correct variable. So think of them as inside, outside, rather than first and second. Even though I just said first integral. Any questions? Yes. Oh, n and m go to infinity. Thank you. Thank you. Now my limit notation is upside down. Oh, well. So it's important that when we write our double integrals from our double Riemann sums, that the integrals correspond. The dx is listed first in dx dy. So the inner integral is going to be the x integral. We can switch things around if we write f at xy dy dx. So if dy is the first thing after the function, then that means our inside integral is the y integral. So if it goes dy dx, the inside integral is the dy integral, and the outside integral is the dx integral. Double Riemann sum corresponds to a double integral in the same way that our single Riemann sum corresponded to a definite integral. Either order works, but there are rules. Sometimes one will be better than the other. Both will always be possible, but sometimes one is just going to be more convenient than the other one. Any questions? Initially, it'll be hard to tell which one is going to be better. It's not going to be as obvious like, oh, I need to drive from San Bruno to San Mateo. I can take 101, or I can hop on a couple of bridges, go over to East Bay. So come down that. Is that 880 or 580? It's something 80. I'll call it N80. Come down N80. It's treating N as a digit. 100N plus 80. Anyway, that one that goes up and down on the East Bay. And still get to San Mateo, but that's not going to be the best way to do it. And the same thing that could happen here. It could be that they're both the same. It's either taking 101 or 280. It's pretty much the same. But sometimes one of them will be taking 101, and the other one will be driving to the East Bay, which goes south on the peninsula. Any questions? Make sure to keep my YouTube videos local so no one knows what I'm talking about, so word doesn't spread. I'm doing like anti-YouTube. I want this playlist only really to matter to like the 20 people that are in the class. My YouTube videos is opposite. Don't smash the like button like it's going out of style. Don't ring the bell. Just click on the links in Canvas. Any questions? All right. Other than that, I think we have calculated some double integrals, even though I hadn't talked about how we build double integrals. Because I said, I bet you can figure out how to calculate double integrals just based on what you already knew. I was pretty much right. All right, so tomorrow we're going to talk about the rules for what we're trying to accomplish when we set up our double integrals. Our double integrals are going to be all about describing the region to the function. We want the volume below a surface and above a region. The tricky part is that a region can have all kinds of different shapes, whereas an interval like we had in Calc 2 had one shape. It's an interval. Start at A, end at B, done. We're going to talk about all kinds of different regions that we can describe for doubling. All right, so that's going to do it for today. I'll see you all on tomorrow. Everybody have a good day, and thanks for playing.